This is one of the most classic examples of a proof by contradiction. So let's assume for contradiction that square root 2 is a rational number, that it is in the set Q, which is a set of rational numbers. So that means there exists P and Q in the set of integers such that, first of all, the GCD of P and Q has to be 1, and the reason why is that we have that square root of 2 is going to equal P over Q. And if the GCD of P over Q isn't 1, then that fraction can be reduced. So it's not going to be something like 8 over 12 because that fraction can be reduced. It would rather be something like 4 over 6, or I guess that can be reduced to 2 over 3. So again, we just don't want a non-reduced fraction because we want to work with things that are unique. And so say this is the reduced fraction version of the square root of 2 as a rational number. So just doing some multiplication, we're going to get that P is equal to square root of 2 times Q. And so that means, well, squaring both sides now, we get that P squared is equal to 2Q squared. And so that means that 2 must divide P squared, which implies that 2 has to divide P. If a prime divides P squared, then it has to divide one of its factors, so it has to divide either P or P, then, well, it has to divide P, cannot divide like something in between because that really doesn't make sense. And so again, it has to divide P, and so that means we have that there exists a K such that P is equal to 2K. So now let's substitute that in. P is equal to 2K, so we get that 4K squared is equal to 2Q squared. And dividing both sides by 2, we get that 2K squared is equal to Q squared. And by the same argument as above, we have that 2 divides Q squared, so it has to divide either Q or Q, and so that means 2 has to divide Q. And so that means there exists a number, let's say R, such that Q, so R such that Q is equal to 2R. And so that means we know that P is equal to 2K, Q is equal to 2R, so now let's go down here. So we have P is equal to 2K, Q is equal to 2R, but let us remember that square root of 2 is equal to P over Q. So square root of 2 is equal to, well, 2K over 2R, and that is not in simplified form because we can actually now cancel out the 2's. And again, going back to one of our conditions, GCD of P and Q is not equal to 1 anymore. This implies that GCD of P and Q is equal to GCD of 2K and 2R, which is not equal to 1, it's actually equal to 2. And so that is a contradiction with one of the founding premises of this assumption right here, that the square root of 2 is in the set of rational numbers. And because we obtained a contradiction in this hypothetical universe where square root 2 is a rational number, we know that that universe cannot be consistent with our universe of logic, and therefore this proof of square root 2 is an irrational number because it cannot be rational.